This video is looking at synoptic chemistry and in particular the links between the ideas of electronegativity and ionization energy, which are both covered in the first year of A-level. So first of all, let's get some definitions out of the way because both of these things are things that we need to be able to define quite clearly. First, ionization energy comes up a lot more frequently as a definition. So if you've not got this learned now, you need to get round to doing that and practice it so that you can just roll this out anytime it's asked for. The definition I've given is for first ionization energy, and we'll talk about the difference between first and successive ionization energies later in this video. So we're talking about the energy required to remove an electron from the outer shell. So we want to talk about taking it from the outer shell. That is why it is the first ionization energy. Each atom in 1 mole. There are different ways of saying this, but the most important things we've got there are 1 mole and gaseous atoms. So we are starting with individual atoms, and it doesn't matter what the element is to start with. So what I mean by that is when we define ionization, we're always talking about removing an electron. It does not matter if it's an element that would normally gain an electron, such as fluorine or chlorine. The other thing to appreciate is that they are talking about gaseous atoms, so we've broken any bonding that is present in the element. And that means, again, if you take something like oxygen or fluorine or chlorine, which would normally be diatomic, they will not be if I'm writing an equation. So for example, for fluorine, the first ionization energy would simply be written as F gas, single atoms, going to F plus gas and losing an electron. How we do that, it doesn't really matter. There are various different ways we can measure this ionization energy, and often it is measured indirectly. However, that's, in a nutshell, my definition. Electronegativity is maybe one that we're not so used to bringing out, but it does get asked. So electronegativity is the ability of an atom to attract a bonding pair of electrons. So already we can hopefully see some similarities between these two things. They're both talking about the ability of an atom to attract an electron towards it in its outer shell, but there are also some differences. And again, like first ionization energy, you may have slightly different ways that you've been taught to say it, and that's fine so long as you get the general idea. So, for example, you could say the tendency of an atom to withdraw a bonding pair of electrons or pull a bonding pair of electrons towards it. However, do try and use the word attract and not the word pull. It's a lot more specific. There is no equation associated with electronegativity. So let's look at how they are similar. Both of these, as we've just mentioned, are a measure of the attraction between the outer shell electron of an atom and the nucleus. So that means that both of these values are affected by the same factors. They're both affected by the distance between the nucleus and the outer electron. So they are affected by atomic radius. The greater the atomic radius, the easier it will be to remove an outer electron, and therefore the lower the first ionization energy. The greater the atomic radius, the less attraction an atom will have to shared electrons in a bond, and therefore the lower the electronegativity. The other thing that's going to affect it is nuclear charge. So atomic radius is an inverse relationship. So we get a decrease as atomic radius increases. So the bigger that radius is, the lower the ionization energy, and also the lower the electronegativity. With nuclear charge, it is a directly proportional, well, it's not directly proportional, it's a relationship which generally says that the higher you get an increase in both of those things, in ionization energy and in electronegativity, as nuclear charge increases. How it's not entirely as simple as that, and we should know that there are some differences as we go across the periodic table, which we will talk about. So what does that mean in terms of trends? It does mean that they have the same trend as you go across a period and as you go down a group. So if we look at going down a group first, down a group, although we do have increasing number of protons in the nucleus, so we do have increasing nuclear charge, we generally have much more increase in atomic radius, which is far more significant. And the other reason that it's significant is because of the increase in shielding. So as well as increasing the distance between the electron and the nucleus, we've also got this increased shielding effect because of all the shells, extra shells of electron in the way. So we've got more shells and we've got more shielding. Shielding just being that effect of the inner electrons reducing the effect of the nuclear charge on the outer electrons. So electronegativity and ionization energy therefore decrease down a group, and there is no exception to that. It doesn't matter which group you're in. So metals, non-metals, group 1, group 7, they will have the same trend. Across a period, you have a different thing happening. So atomic radius actually gets smaller across a period, and the reason it does that is because nuclear charge increases. And because nuclear charge increases, but we have the same number of shells, and so the electrons are generally actually getting closer because they're more attracted to that nuclear charge, then that means we've got the same amount of shielding as well. So in general, electronegativity and ionization energy, or first ionization energy, increase as you go from left to right. Now this also fits in with our real basic kind of GCSE science ideas that as you go from left to right, things go from metals to non-metals, and non-metals are more likely to gain electrons, and metals are more likely to lose electrons. This is really telling us these two trends, because metals have got the lowest first ionization energies, which means they're very likely to lose electrons from the outer shell because it doesn't take much energy. And it's also telling us that non-metals tend to attract electrons towards them really strongly, which is telling us that they're more likely to form negative ions. So this is how we make predictions about ions that form. We don't just go, oh, it's a metal, it always does this. Actually, it's about these ideas of first ionization energy, or second or third, and also electronegativity. So when things are similar, the problem is we can use them at the wrong time and we get confused. So we do need to understand that there are some differences as well. So a very simple difference is that first ionization energy, or any ionization energy, has units of kilojoules per mole, whereas electronegativity, which is shown on this table on the right hand side, has no units, and in fact it's a very arbitrary scale, and you don't really need to know how it's worked out. The other thing to notice here is that there's a much bigger difference. So it's a very wide range of values for ionization energies, which means we can find out a lot more detailed information from ionization energy than we can from electronegativity. Electronegativity, as you see here, actually only ranges from about 0.7 down here with our francium and up to 4 with fluorine. So really that's a very, very narrow scale with which to judge the ability with which an atom can attract its outer electrons. Another thing to notice is that electronegativity has a steady increase across a period. So, for example, if I were to take group 2 and compare it with group 3, the electronegativity increases all the time because of the increasing number of protons in the nucleus. So aluminium is more electronegative than magnesium. That is why, in fact, aluminium can form some covalent compounds with certain nonmetals. Meanwhile, if we look at our first ionization energy graph on the left-hand side, we will always see between group 2 and group 3 a little drop. So group 3 first ionization energy is lower than group 2. What that's showing us is the difference when we go from the S to the P subshell. So for aluminium, for example, the outer electron is in the 3p subshell, whereas for magnesium it's in the 3s. S is closer to the nucleus. So we can see, because it's a wider range of values, we can see the difference going from one subshell to another. And we can't see that with electronegativity. We can see the difference in shells, big difference there. As we go to a new period, electronegativity goes down very substantially. But we don't see it, those little drops, and we also don't see it between period 5 and 6, sorry, group 5 and 6, so nitrogen and oxygen, whereas for ionization energy we do, and that's to do with paired electrons in p orbitals. So we don't see any finer electron structure. And that helps us decide when we're going to use electronegativity and when we're going to use ionization energy when we're explaining how atoms behave, what they do in terms of electrons, whether they lose, whether they gain, whether they share, and also about atomic structure. So in the last bit of this video, we're just going to look at when we use each term, because the problem with them having similarities is we can mix them up. And I think the word electronegativity is used wrongly quite frequently. So when do we use electronegativity? In a very broad sense, we can use it to determine the type of bonding. And this may have passed you by, but if there is a large electronegativity difference, you will get ionic bonding, and if there is a small electronegativity difference, and in here we're talking about nonmetals, you will get covalent. So most of the time we would just go, okay, well, metals and nonmetals is covalent, but that is because metals have low electronegativity and nonmetals have high. Just an example of where this is relevant, aluminium fluoride is an ionic compound, whereas aluminium chloride is covalent. And you may have come across aluminium chloride. It's used a lot in sort of shapes of molecules and stuff to do with dative bonding and things like that. It's also used in benzene chemistry, which you may not have come across yet. Aluminium fluoride is ionic because fluorine has a very high electronegativity compared to aluminium and is able to withdraw the electrons so much that it becomes ionic. So it's pulling electrons so much towards it that it actually forms a negative ion. Chlorine, next element down the group, is less electronegative than fluorine. Aluminium is a relatively electronegative metal because it's in group 3, and so there's a compromise. They share. However, we know that they're not going to be shared equally, and that is the main time we will use electronegativity is to predict, I don't know why my pen keeps disappearing on this bit. We're going to predict the polarity of bonds. So we're using it to decide which one is delta negative and which one is delta positive, and that should be obviously limited to talking about covalent bonds. So when should we not use electronegativity? Because I mentioned that sometimes we use it in the wrong contents. So we should not be using it to talk about strength of covalent bonds, because that is about the length of the bond and the strength of the attraction, and is not to do with how polar it is, although they are indirectly related. We should not talk about electronegativity. If we want to talk about reactivity, that's not generally an explanation for reactivity. Okay, when do we talk about ionization energy? A lot more. Make sure you do some practice questions where you know the kinds of things that might come up. So we could talk about it when it comes to reactivity of metals, particularly group 1 and 2 metals, because the lower the ionization energy, the more likely they are to lose electrons. And so that's obviously important because group 1 and group 2 metals lose electrons when they react. It also sort of tells us whether something forms a positive or negative ion. So we've already sort of mentioned that. So very small electronegativity and very small ionization energy will therefore form positive ions. High first ionization energy is more likely to form a negative ion. And it also gives us an idea, like explains why things make the charges they do. So we can predict the charges on ions. For example, sodium has a relatively low first ionization energy and a very, very high second ionization energy, and that is because the second electron is in a shell much closer to the nucleus. So this is also how we use successive ionization energies, first, second, third, fourth, fifth, etc., to determine like how many shells an element has and how many electrons it has in its outer shell. So wherever there's a huge difference between ionization energies, it's because it's in a shell closer to the nucleus. That means that sodium will not form a second charge. It will not form a 2+ ion because its second ionization energy is very high. That is a much better way to explain it than simply saying it has a full outer shell. And then we can also explain why, for example, transition metals have lots of different charges. That is because their ionization energies are all very close together. So it doesn't make much difference between making a 2+ and making a 3+. So that's where we use ionization energies, and as we've already mentioned, we used first ionization energies to tell us about subshells and orbitals, and that is the most likely time that you will get asked about first ionization energies, is in that